is the following. I have this piece of code which I wrote following the book Build Your Own Lisp by I don't want to mispronounce the author's name. I'm really sorry. Let me just take a look. Daniel Holden. It's a great book. I read it because I'm mainly a web developer trying to learn new technologies and trying to remember the technologies I used before. Okay, so what do we have here? Yeah. Okay, I want to debug this. I can. This is how I put breakpoints, right? What line is this? Let's go all the way. 264. 264. Is it run or start? It's run. Is it run? Okay, it started. Nice. So what do I have here? Yes, this will be my input. This guy right here, +2, 3, 3. Times 3, 3. Okay, so we are starting. This is the line during which at which the debugger stopped. Basically, the first line, the one we tagged with the debugger. So what I'm gonna do? Let me just take a look at something because I don't know by heart. I think I've written it here somewhere. The difference between next and step. Step into function call, do not step. Okay. I want to step, I want to go all the way. So it's S. Okay, now we are inside. I will read in this file. And it's this one right here. Is it this one? It is. So string, substring, t tag number, t tag symbol. So what do we have here? Print. I think this is the root. Yeah, this is the root. So what will happen here? If I click next, it's not a symbol, or is it a symbol? Print t. Is the symbol? What else do you have inside t? It has this NPC abstract search tree type, has a tag, some contents, a state, number of children, and the children itself. Okay. Okay. So I'm just taking a look at it. So what do we have here? It's the contents. So yeah, this is the root node, right? So this will also fail. Ah, yeah, here it takes a look at the root node. And basically, if I'm not mistaken, it will create an S expression. So let's step in. Where are we exactly? Step in this guy. What? Where am I? It's now step. Next. Oh. Sorry. Wrong place, wrong time. Finish current function. Finish. Is it finish? Oh, I'm here. Okay. So can I now go inside? Step. Yeah. Okay, so this is the LLS expression method. At line 61. Where are you? Oh, it just creates. Okay. We'll just create. Let's finish this. What? Finish it. How do I do not step into function calls? Okay, let's just leave. Next. How do I finish? Okay. Okay, where are we now? At line 224. It's here. So now I think I just go next, nothing will happen. Finish, can I just finish it? Yes, where am I now? 264. Okay, so 264. So I think I got the basic workflow of the script. I understand the way it works, but I just want to go through the whole flow. I want to make sure everything is quite clear. Okay. Where am I? 64, where am I? It's now this. Okay. Yeah, so we finished. Pardon, we finished read. So now we are here at line 208. Where are they? Here. Where Where is this method? Okay. Now 211. Wait. I should have broken these snippets into multiple lines. But what can you do? You make mistakes. Main. So where am I here? Ah, here. So what's gonna print text, right? And what's sex? Where am I now? 266. What's content? It's symbol, right? No, it's what? Oh, we skipped everything. Clear. Okay. No, leave this. For some weird reason, it skipped all of these. It skipped because I think most of these are okay. Most of these are recursive functions. So when I pressed next line, I skipped all of these completely. I assume. Okay, let's put maybe here at 220. At 220. Break 220. Run. So what's gonna be +2 times 3. Okay, what do I have? Print the tag. Okay. Finish. Print the tag. Why is 220? Print. What do I have here? Contents. It's empty. Okay, let's go. Finish this one. Print the tag. Print the contents. Why? It's the same guy. It is the same guy. This is the same memory address. So next. It's neither of these. Right? Yeah, it's neither of these. Oh no, it is. It is. Oh, okay. No. This has the form of a search tree. It's not continuous. There are no one after another elements. It has the structure of a search tree, meaning that it branches out. That's why I basically once we send the error output, this is the okay, I completely misunderstood. I completely misunderstood. So what I thought, that's this it. Let me pick green. I think this is starting, what's the name? The starting symbol, the root of the search tree. So what do we have here? We have a plus, right? How does it work? It's like this, plus, sorry. Wait. Let me create the language. So it's what I have. I have this. Plus the rest, right? Okay. How would a search tree look like if our Lisp based input is +2 times 3. Come on, man, don't give me the fluff. Give me. Okay, yeah. I just misunderstood it because, okay, so we'll have the root. We'll have the root. Then we'll have the plus. And the plus. Where are you? We'll branch to 2. And this all, but this all will branch into 3 and 3. Okay. Simple, easy, understandable. Okay, let me just move it back to the code. Okay. So what's happening here? What goes on inside here? What? Okay, so sorry, I'm thinking. Okay, so this is our tree representation of this simple Lisp-like construct. Okay, this is our tree-like. And this whole tree is actually the parameter to these two methods. So what actually happens here is this line goes here. And then we hit the children. And then we read. Yes. Okay, so this a recursive structure. Okay, let's print out some shit. Let's print out some shit. Okay, I will read what line is this. This is 220. Break 220. Run. I don't need this. Okay, now this is what I'm talking about. We have completely different memory addresses, meaning that we hit another iteration of this method. So print, what's your tag? It's an expression or a symbol or a car, which I assume expression or a symbol. Is this based on my creations here or print based on member name content? What's the name of this member? Contents. It's a plus. Okay, so now we are here, right? So let's test something. So it's it should have children. It should have the plus should have 2 children. Okay, where's the code here? It's not a number, it's a symbol, it's plus. That's why we have plus. Then we continue this. Print. How many of you are children? So children, none should be 2. 0. Why? What's 0? Maybe I just need to add them? No, it's not it. Okay, let's do this again. But so I always keep coming back to the way the language is created. I get confused at I don't know a certain point, and then I just want to come back to see how this actually works. It's multiple expression. The first expression is a symbol. The first symbol is a plus. Multiple expressions. The next is the 2, right? The next is the 2 because it's a number. Next we also have an S expression which can. Oh, okay, now this makes sense. Getting it now. Getting it. But then why doesn't this work? Hello. I'm looking for the number of children here. Okay. And according to calculations, if we are at the contents, if we are at a place in the abstract search tree in which we have a plus, we should have two children, one of them being the number 2 and the other one being this whole being this whole other expression. Right? But the print but this won't work. It has no children. Contents. Because it's not children, is it? It is children. Children. Ah, no, it's... Wait. Yeah, but this should work. It's an array. Ah. I have it. It was so a mistypo. I can't access it because it has no memory. Why? Where am I? Print the tag. Print the content. Print the contents. It's a plus. So it should be okay. It's a plus. Next. Nah. Continue. What's this? This is gonna be a 2, right? It's a 2. Why didn't the plus have any children? It should have. The children of the plus are the 2 and the other why didn't it have any? Okay, that's a mystery. Now the 2 shouldn't have any children, right? Children none. It's 0, yeah. Continue. Now this should be the multiple. No, it's not the multiplication sign. Why? How is this created? Pi. What? 5. Ah, it makes sense. Right? Does it make sense? 1, 2, 3. 1, 2, 3, 4, 5. Or is this plus? Okay, let's just do this. Let's just do this. I just want to see how this is created. That's the only thing that interests me right now. Okay. Based on this natural language. And this being the way we parse the language. Can you explain me step by step how would this example plus 2 times 3 be parsed. Okay. 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 I don't care. I've been over this hundreds of times. I don't need this. The entire string is treated as a sequence of expressions. Okay, then the parser will split input into tokens, recognizable tokens. This is the plus, this is the other plus, this is the third plus, and now this is. Okay, so these are on the same level. Okay. But then why does the abstract search tree look vastly different? Maybe because the abstract search tree. No, but doesn't make a lot of sense. Doesn't make a lot of sense. Okay. Wait, how? Did I have any free space between the inputs? I did have free space. Okay, okay, so this actually makes sense. What's happening is that okay, so what's happening here is the following. Let me just pick another color. All of these are tokenized. This is tokenized as a whole, and then it's tokenized like this, right? So this is how the parse tree would visually look like. But my question is, why? So this is an incorrect representation of the abstract search tree. How would an honesty work based on this sign? Oh, yeah, yeah. So it's like this. It's like it was like this the whole time. Just like this the whole time, definitely. Okay, I'm gonna do a quick test of this. Let me just get my water. Sorry. And I'm back. We had a quick ad break, and we are continuing. So, should I start this from the beginning? No, I won't. So this one has 5 children. Whatever node we are at has 5 children. Is it this node? Is it the S expression node? Print t tag. It this an S expression? Where am I now? 220. Is this 220? Yeah. Expression, S expression. So if I start like this, children, 0, I think I'll see the open parenthesis. Yeah. 1, it's empty space. No, it's this guy. Ah, yeah. Now it's an empty space. No, it's 3. Wait, how did I write this shit? Okay, so it ignores empty space. Okay. Another 3. And the closing brace. 5 children. 5 children. But what is happening with this node? What's happening with this node here? Not git. Not git. Expression as expression or this. So what will happen here? No, this won't trigger. It won't trigger this line either. Won't trigger this one, but it will trigger this one. So now X is a type. How is it called? How is it called? Type. Yeah, it's type. But I don't know what type this. It's 3. It's 0, 1, 2. It's an S expression. So basically now I'm creating an S expression. And I'm not caring about these guys. I'm not caring about parentheses and braces. Why? Because what is 0? Yeah, it's the open brace. So it's gonna ignore all of this. And it's just gonna add. It's gonna add the Lisp value. And then it's gonna call the read on each and every one of its children. Wait, next, where am I? Children, oops. Wait, what is E now? It's 1. Next. So what I was looking at is I was wondering why I didn't reach this line. It's because we have the continue here inside the block, basically skipping every one of these symbols. So now, if I'm not mistaken, is it contents? Contents. It's a star. Okay, this one won't be skipped. I'm gonna go next. Okay, here. What's X? Okay, so X. I'm just basically creating this same underlying structure again, or at least a similar structure. So what will X do? Where's Lisp value add here? It will increase the list of children. Will it? Yeah, it will. It will. It will. So it will reallocate. Okay, okay, this is really fun. So what happens now is if I do skip, am I gonna end in, I think I'm gonna end in this one. But basically what's happening now, can I break at, what line is this? Break at 97. No, I don't want to do this. What if I step into, yeah, it's read again. Wait, why am I calling him again? Ah, I'm just reading, okay, I'm just reading the node again. I'm just reading the node again, and I'm just basically looking at it. Yeah, so this will actually return this x, and then we will, in the parent method, we'll add lval with the x, which is the parent, which is the one that has 5 children, and the other element will be this, but it will reference the new Lisp value that we create from this element, which is the multiplication string. Okay, simple enough. Right? Right. Oops. It's a symbol, is it? It's the symbol. Yeah, it is a symbol. So basically, nothing happens. You'll just create a new. Where are you? Where are you? Where are you? Here. We'll create a new Lisp value type, but using this method. And where is the symbol method? It's here. It just creates a new value of this, and then the new value will be added. Okay, okay. I think I get it. I think I get. I think I'm really grasping it. I mean, not still. I'm not having 100% on it, but it's getting better. Okay. Maybe I should do this by hand. No, what is the difference between a stack and a heap? So basically, I'm right now in the book looking at the bonus mark section, which asks some questions about the chapter that we just finished. The first two questions are asking to give an example of a variable that lives on the stack and a variable that points to the heap. So let's just refresh my memory on these two concepts and I'm gonna answer it. Am I using the meaning? Oh. The difference between a stack and a heap pertains to the way memory is managed, allocated, and accessed to computer environments. Okay. Each serves different purposes and has unique characteristics. Here's a detailed breakdown. Stack. The stack is a region of memory that stores temporary variables created by each function, including the main function. It operates on a last in, first out. Last block of memory allocated is the first to be freed. It naturally supports. Okay. Each time a function is called, a new block is reserved on the stack for local variables and some bookkeeping data. And heap is a region of memory used for dynamic memory allocation. Blocks of memory allocated and freed in an arbitrary order. Unlike the stack, the lifetime of memory in the heap is not determined by function calls, allowing the flexibility of manual control. Okay. Stores temporary variables created by each function, including the main function. Okay. Can you give me some variables created that live on either stack or heap? Variables created on the stack are typically those that are defined within the scope of a function local variables. Their lifetime is limited to duration of function call. Yeah, so basically I wanted to point out some of these here. For example, this is a stack variable because it only lives while this method lives, right? Yeah, while where are you? While the scope of the function is visible and the lifetime is limited to the duration of the function call. Like this. Because these two variables are created and destroyed within the lifecycle of this method. Okay. Okay, so this is the way we allocate variables on the heap dynamically. Okay, simple enough. Simple enough. The next question. It asks, what does the string copy strcpy, what does the string copy function do? If I'm not mistaken, where do we have it? Here. But I don't want this one, I want this one. There are multiple instances of it. So, what string copy does is copies a certain content of a variable inside a previously allocated memory address. Let's see if I'm right. I think I am. What does the string copy function do? Used to copy the string, including the null terminator from the source string to the destination string. The signature of this function is typically defined as this. Yes, yes. Okay. What? Oh, it's still running. Okay, let's read through it. Copying process string copy the character from the source string to the destination string until it encounters a null terminator in the source string. Okay. Okay, these are extra information. Some of those I don't need right now. So okay, here's a simple example. Okay, simple as that. What does the real alloc function do? Okay, again, I have no idea. I know we used it here. Here it is. So the shortcut realloc, I assume means reallocate, which will, again, it is an educated guess based on how the method looks and the name of the method, which will do the following. It will get a certain memory address, right? And it will create space based on whatever criterion we add to it. Let's see. Resize a previously allocated memory block. The function is part of the C standard library and is declared the standard library header. It allows you to increase or decrease the size of a memory block that was previously allocated with malloc or calloc. Yeah, basically moving it to a new location if necessary. So this is the memory block, and this is the new size. If new size is greater than the original size, the additional memory will not be initialized and the original content will be unchanged. Okay. Okay. Okay, I get. Let's do another one. What does the memory move function do? Where have you used it? I saw it. Oh. So what's the difference between this? Just moves and or displaces a chunk of memory to another memory location, right? It should be it. I'm 100% sure. Copy a block of memory from one location to another. Yeah. Handling cases where the source and destination blocks overlap. It's part of this. Okay, so it does the additional work of handling overlaps. Unlike memcopy, which does not handle overlapping memory blocks safely, memmove ensure that copying is done as if the bytes were copied to a temporary array first. Okay. Actually, one of the questions basically states how does memmove differ from memc? But wait, what is the difference? Okay. One allocates memory, and the other one moves it around. There is an extra question saying extend parsing and evaluation to support the remaining operator modulo. Okay, maybe this isn't such a bad idea. Okay, remove this guy. Mm. So at one point the Lisp value should hit this line. Let me just test this. Get it, GD bugger, error handling, break 181, run. Plus 2 times 3. Here we are here. Print v count. What do you have? You have 3. What do you have? 3 of what? Print v cell 0. Is it cell? Yeah, it is. 0. What's here? It's 2. It's a symbol. Print v cell 1. Content. What? It's a symbol. It's a plus. No, it's not a plus. It's the number. It's 2. Oh, I misclicked the. Okay, so the 0 should be a plus, right? Yeah, 0 should be a plus. So I know basically. Okay, let me just maybe. I don't know how this structure looks. I don't know. I don't have dual data, but it should. Just stop. But it should be like this. Let me just pick another color. I don't know. Let's pick blue. So what do I have here? I have V. And V is unknown, but I know that V has 3 cells. V is like a parent root element, but V has 3 elements. The first one. Okay, let me just maybe do this, write this better. Okay, where are you? The first one has the type of, sorry, a symbol, and it's a plus. Yes. Now the next one. It's a number. So this is, no, it's not a symbol, it's a number, and it's 2. Now, it's an S expression, right? 0, 1, 2, 3. Yeah, this is an S expression now. Oops. And it has no content, but now S expression have content of its own, right? Let's try this. Print v cell 2 count. It's 3. It has 3 elements. So in a weird act of solidarity, it will have a 0 here. It's gonna be symbol, and it's gonna be the multiplication number. It's gonna be 3. another 3. Okay, okay. We have it here. We have it here. So I'm here right now. Where am I? I'm at 181. So now we are evaluating the S expressions we have. Okay. Let me just get my water again and we are continuing. All right, let's keep it. So where am I right now? Line 181. Just a second, please. So next. Okay, we are assigned a loop. And inside this loop, which is on line 182, which is this line, we are checking for every element of the Lisp value to evaluate it further. So each and every one of these elements is gonna hit this method. Again, this seems like a pretty simplistic method. Maybe we could even integrate it here somehow, but okay, I know what. Well, my mind is opening. My mind is widening. Basically, what happens here? We go through each element at one point, and it will be, in this example, we're gonna hit another S expression. So basically, this method just evaluates the Lisp value, and if it is the type Lisp expression, it triggers this method again. Basically, this creates the recursion, even though it's found in two different methods. Yeah, that's it. So next, again, next. Oh, not next. I should have used a step. Print v cell e contents. No, it's not content. It's type. Let's proceed the type. It's 3. It's the S expression now. Okay. Let's break 181. Run. No. Okay. So it's not next. It's next. 181. Where are you? You are here. So it's next. Or step. No, it's next. Right. It should have been step. Next. We are here again. It's 3. Should be a plus. Right, it's a plus. So why are we here again? It's step. It's not the same. It's. How can I restart this? No. I need to read code better. So basically we have two loops. Okay. I think I get it. I think I'm starting to understand it. So now, drum roll, please. We are picking up another chapter. This chapter is called S expressions. So, chapter 10. So what I will do just right now is copy chapter 08, name chapter 10. Yeah, I need a recursive one. Yeah, this. I'm gonna remove error handling, and I'm gonna move this to cool expressions. No, is it called CC? So this will be cool expressions, and the executable will be also called cool expressions. Okay. So what are Q expressions actually? So it's a new feature that we will add to our code, and it's a new type of Lisp value, and it's called a Q expression. This stands for, it says here, quoted expression, and it's a type of Lisp expression that is not evaluated by the standard Lisp mechanics. Okay. When encountered by the evaluation function, Q expressions are left exactly as they are. This makes them ideal for a number of purposes. We can use them to store and manipulate other Lisp values such as numbers, symbols, or other S expressions themselves. So, okay, let's do it here. I don't know, give me this green one. Chapter. Sorry. Let's do it again. Where's the center of this? Is it this one? Yeah. Chapter 10. Cool expressions. Okay. So what are cool expressions? Second. Okay, I opened the book by mistake. I opened the book by mistake. Sorry, it wasn't mine. So the book said, 'Q So co-expressions. Not evaluated. So just drop that, but okay. So they are not evaluated. So they are most commonly known as lists of data. They are used to manipulate code. Oops. Code. Okay. Okay. The simplest things that we need here are here. After we added Q expressions, we are going to implement a concise set of operators to manipulate them. Like the arithmetic operators, these will prove fundamental in how we think about and play with expressions. Okay. Instead of parentheses, we are going to use curly brackets. And this will be the difference. So, in the book, there's a block of text saying, I've never heard of Q expressions. And Q expressions are not found in other Lisp languages. They use macros to stop evaluations. Okay, so either macros or Lisp evaluations. And the first thing is, let's change our grammar. Let's get it down. Let's do it just a second. Okay. I'm thinking about something. Yeah, I just wanted to open the book in another tab. So, I want this to be here. Yeah, okay. So now we can write, like I follow the book actually on my other tab. So what we need to do when it comes to grammar terms, changes. So what do we need here? New parser. What else? Define the parser. And clean the parser. Okay, these are the changes. So let's go to the code. Oops, I need this. How can I move it here? Also, I don't need it. I only need this. Okay, so first things first. Let's add a new parser. Okay, just a second. Okay. So what will I do? I need a new parser. I need a new parser, and I'm gonna define it as follows. MPC parser E. So what is this? This is Q, but I need this above, not here. Just under TS expression. Parser T Q expression. Okay, I have this. Next. So wait, is this chapter 8? Okay. Ignore close ignore bin file. I think it's Q, right? It should be Q. It's Q. Yeah, because we are not doing this anymore. We are going to chapter 10. Now we have cool expressions.c. And now we'll add our changes here. Again, MPC parser underscore T cool expression. Okay. Next. Should have a cool expression here, and this is what I wanted to do. I wanted to move all of these to be in the same line. Okay, now what do I have? I have this. What do I have here? I have an expression, right? Like this. Here I'm having this. I'm closing it. I'm wrapping this up here. So numbers, symbol, S expression, Q expression, Lisp, and I'll also clean it up. Okay, I also cleaned it up. Okay, so what's next? Next. I still. I'm still having a bit of a confusion here. Wait. So where is the, I have a GPT open here somewhere. No. Give me an example that portrays the difference between and S expressions in Lisp. Okay, I just want to make sure I know how different they are. What is the basis for the difference? S expressions are the fundamental building block of Lisp syntax and are evaluated immediately when processed by the Lisp interpreter. Immediately. An S expression typically consists of a function followed by its arguments, all enclosed in parentheses. Q expressions. They are not evaluated immediately. Now, here I get confused. Why? What does this mean? They must be explicitly manipulated and evaluated using specific functions. It's a dot. Ah, okay. Okay. So Lisp is a primitive language. The syntax is not. It's not the strongest point. Okay. So what the good developers thought is the best way to represent a data structure or a place where we should store information is by doing the same old S expressions, but adding, for example, was this a quote mark, which isn't so smart. I mean, maybe it is. Maybe once you get really involved into Lisp, maybe you became an expert or something. Okay, I don't care about these things now. So let's add a new type here, right? That's one of the first things we need to do. Here, number, error, symbol, S expression, and Q expressions. Okay. And we can also have a constructor. I'm gonna add it below its little brother or big brother, I don't know. Which one are used more? Q expressions. It's gonna be the same old. We are creating a new Lisp value, allocating the size. The type will be the Q expression, right? The count will be 0. The cell will be null and return V. Okay. Oops. Okay. So this is the new constructor. Now, we need to print them as well, right? We need to print them. Where is the print method? No, this is the delete method. This is the take method. This is the print. Here's the print. Okay, depending on the type, at one point, you're gonna evaluate whatever input we provided, and it's gonna come across something that is a Q expression. So what should you do? Oops. No, not here. Case Q expression. Expression print, but printed like this. Ah, I'm so smart. Break. We can. Where is the delete? It's also deleted. Where is it? It's here. I think we can just do the following. Is this working? Case Q expression. Okay, I like this. Okay, so let's stop. Let's stop here. I'm gonna save this. I'm gonna cancel it as well, because what we'll do now is some of my favorites. Reading Hacker new articles. Just a second. Oops. So I can move this. I can also move this. This is my tablet. There's nothing on it officially, not yet. This is Hacker News.